All right. Okay, so hopefully we're live, waiting for YouTube signal. So today, what I wanted to do is try and calculate to see if my theory of dark matter explain dark matter, explain the. All right, audio is good. Just to see, I want to see how far I can get in the calculations of dark matter. So let's look. Let's see if we can figure this out. So let me just explain again my theory of dark matter. Let's draw. No. Let's draw whiteboard. Blah 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 blah. Create new. This is dark matter. Dark matter. So dark matter has been unexplained as of yet. We don't have, I didn't hear of a good explanation of dark matter. They say it might be a particle. I don't know. It might be. They say that's the most likely thing. All right, but I think maybe we can try and explain it using ether. Ether as aether-flux as a gravitational phenomenon. So let me explain. So let's say you have, it doesn't matter what, it could be a galaxy, it could be a planet, it could be a single neutron. So it doesn't really matter. It's some mass. Something that has mass due to interaction with the Higgs mechanism. So it has mass. Okay. So because it has mass, then GR says that it curves space-time, to which I say that's a misinterpretation of the math, but it doesn't matter. I mean, I agree with GR. I'm not disagreeing with GR. I'm just disagreeing with the interpretation. So it doesn't really matter. So I say there is flow of ether. Einstein in 1920 said it's ether. The fabric of GR is the ether, but it's not flowing. Okay. So I say it is flowing. And I don't need GR for that. That is the only explanation why the apple falls from the tree. I never heard of an explanation why the apple falls from the tree. The only explanation I ever came up with is that ether flows through the apple and pulls it down. It's a force. And the apple is actually waving upwards through the ether. The ether falls down at about 11, my calculations show it's about 11,000 meters per second at the surface of the Earth. All right, so we're all waving through, which is in accordance with QFT. I'm not saying anything that contradicts mainstream science, I don't think, except for, minor interpretations, minor differences over interpretation. All right, so how does this explain dark matter? Right, so dark matter, let's go over the phenomenon, is the phenomenon by which when we look at galaxies, the rotation, I mean the speed of the stars in the galaxies, they're moving too fast. they're moving too fast. Hold on. Let me ask them if it's urgent. 1 second. Give me a second. Just 1 second. Oh my God, it takes so much time for the system to load. Come on. Loading. Everything is loading. Okay, it's going to take a couple of minutes to load. What is going on? Jesus. Everything is loading, 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 loading. Where is... Oh, I need to scroll. Okay, so here it is. Second. All right, let's get back to this. So, okay, so galaxies, so according, I don't know exactly what I think we expect the curve to look like this. This should be 1 over r squared. Shouldn't it be 1 over r squared or something? I'm assuming they did the calculations and they got the wrong, and empirical results are not matching the theory. The theory should be fairly straightforward. It should be fairly straightforward to calculate the motion of the stars, the speed of the stars, the angular velocity. So the stars, as you get close to the outer rim, the stars seem to be moving too fast. The galaxy should be ripping themselves apart when we look at the speed of the stars. So there seems to be an extra mass. The galaxies seem to have extra mass spread, I guess, maybe evenly. I don't know. There seems to be extra mass that we cannot account for it. We don't see it. But it's supposed to be, I think, 75% of the mass of the galaxy seems to, we cannot account for it. We don't see it as stars, as black holes, as dust, we just don't see it. So it's missing. 75% of the mass is missing. Okay. Is this 1 over r squared? No. If this is r, 1 over r squared looks like this. So this is maybe the way the speed should basically look like. And I think instead, it probably it flattens out. It's too flat. The speed here seems to be the same as the speed here, which should not be the case. As we go farther and farther out, the speed should slow down. Okay, I'm assuming they got the numbers correct. I'm assuming that they went over the numbers and they got the numbers. They have whatever numbers they collected, the data they collected. I'm assuming they didn't make too many mistakes, and the stars are flying too fast. As you go to the outer rim, it's too fast. I'm assuming in the inner part of the galaxy, there is no issue. Okay, so we need a lot more mass. For every galaxy to have more mass. That's what I think. That's, as far as I know, that's what we need. So for now, scientists have come up with dark matter. They say, okay, there must be dark matter, and if we add dark matter, it stabilizes the galaxies, but we cannot account. So the accounting, we know what's missing. We can't find it. Okay, so let's go with that. So we just need to add more mass. Okay, so here is a piece of mass, and according to general relativity, Newtonian, or just based on observing apples accelerate towards the ground, so there must so something must be flowing into masses. Okay, so if we assume that, that's the first assumption. Second assumption, it must be fairly fast. So if it's Earth, it's at about 11,000 meters per second. So the speed of light is 3 million meters per second. So it's 300 million. So 30 million would have been 10%. 3 million. Oh, it's not relativistic by any account, by any stretch of the imagination. It's not relativistic. Okay. So for Earth, we're not talking about relativistic speeds. The question is, for the galaxy as a whole, could it actually have a relativistic effect? Okay, what? The question is what? So my answer is, okay, so something is flowing, but what is flowing is just the ether. But the ether has in itself has a mass, but besides the ether having mass, the ether itself has a non-zero energy. The ether itself is always fluctuating, as is noted by Heisenberg's uncertainty, and just what scientists call the quantum foam. And this thing has many names, and it's been the Casimir effect. We know we have enough evidence for this phenomenon, so we know it's real. It's documented. It's measured. So we have this phenomenon. Okay. So what does that mean? That means that the ether has a mass. It has particles, actual particles. You could say it's virtual particles, but they have virtual mass. So it's mass. I don't know what virtual means. So I have to assume, right? It's not just me. I mean, one of the explanations for dark energy is the quantum pressure, is this very quantum pressure. And they say, okay, that's giving us too much energy. Okay, so at least it must have some mass. Let's go just with the mass that the ether creates through Heisenberg's uncertainty, through Casimir. No, Casimir effect is Casimir effect is a measured. That's one way to measure the quantum foam seething, and therefore having a mass. So let's assume it has a mass. Okay. So it has a mass, and it's flowing fairly fast, not relativistic when it comes to Earth. When it comes to the sun, if we do the calculations, it might already be relativistic speeds. Certainly when we talk about neutron stars and black holes, those are relativistic speeds. The question is, when we look at the galaxy, can we estimate estimate this velocity, the velocity at which the ether impacts or is annihilated, it flows. Forget about annihilation for now. The ether flows into the galaxy. So let's assume the galaxy, let's just take the galaxy as one bulk, one massive bulk. However much is its mass, let's average it out. Let's have an average density, average mass, and see what is the speed. What is the speed of the ether as it flows into a galaxy? So we'll take that number. So what's the ether speed? That would be the speed, the velocity. Then we can take the mass density of the quantum foam, and then we can see if the mass density times the velocity, so that should give us a momentum density. The question is, okay, so we would have some sort of, right? So this momentum density, then we'll see if it's relativistic, we'll increment it relativistically. Now, do we need the relativistic effect? I think we need the relativistic effect, because if we're not getting a relativistic effect, then the galaxy is not going to have an extra mass. There's no extra mass compared to the intergalactic space. The intergalactic space has just as much quantum foam as the galactic space. So we need to give the galaxy extra mass. So in order to give it extra mass, we need to take the same stuff that is in the intergalactic space and give it extra speed, extra velocity, so that we have an extra momentum, and then give it, calculate the relativistic effect. Maybe that will give us enough mass. We need to be able to add 75% on top of the mass of the galaxy. I think we need another 75%. The question is, can we get that? Are those realistic numbers? I don't know. But that's the direction. There's many unknowns here. No, actually, there's just, there's basically one big unknown, and that is the mass of the quantum ether, the quantum foam. So that's the biggest question right now. Okay, so how do we figure this out? So let's go to YouTube. Let's just try and let's try and calculate Let's try and calculate the mass of the quantum foam. Can we just calculate the quantum foam from 9 years ago? Okay, so he tried to calculate it. Let's try and see what we can get from that.
Fundamental governing rules of the about 100 years ago. Our understanding of the fundamental.
I hate people that wear t-shirts with a jacket. Like, if you're gonna wear a jacket, please wear a shirt, a collared shirt, hopefully long sleeve. It's too annoying. Also, this YouTube video is from a long time ago, so the quality is low and the audio quality is low.
Governing rules of the universe changed in a radical way. Rather than the simple and relatively intuitive world of pendulums and pulleys, Newton's law of gravity and Maxwell's equations of electromagnetism, the discovery of quantum mechanics and Einstein's theory of relativity showed us that, at its core, the universe behaves in rather unexpected and non-intuitive ways.
I don't know why he says that. What do you mean unintuitive? Like, if you ran the universe, would you change anything? What would you change? What is unintuitive? Why do you say that? Like, the more I study modern physics, the more intuitive it becomes. I don't see what's unintuitive. Maybe in the beginning it's unintuitive. It's not in the beginning. It's like when you listen to a lot of YouTube and experts explaining modern physics, it's nonsensical. But the more you study, the more sense it begins to make, and the less unintuitive it becomes. It becomes extremely intuitive, and I don't know how else you can run the universe, how else you can have a universe, if not through modern physics. So I don't know what you mean by that. I don't know why they keep saying this. It's like, okay, maybe there's things we don't yet completely understand. That's fine. But, you know, that's always been true, probably always will be true. There's always going to be cutting edge research. So, you know, like a long time ago, nothing was intuitive. They didn't even know how life began. Today, we know life is boring. There's nothing exciting about the research into how life began. It's really very straightforward, one way or the other. It's really very straightforward. Consciousness, for most people, I guess, is eluding them. For me, it's not. For me, it's boring. Just another day at the office. So anyway, let's continue.
We learned that moving and stationary clocks tick at different rates, and that Schrodinger's cat was simultaneously dead and...
Neither of these statements is... I disagree with both these statements, but never mind.
alive. These ideas, and others like them, have bothered scientists, both professional and amateur, for nearly a century. In fact, it's unusual that a week goes by when I don't receive an email or letter from some curious soul who thinks they've found a fatal flaw in the theories of quantum mechanics and relativity. It is very rare that these communications include an idea that wasn't asked and answered years ago. The simple fact is that while these theories are counterintuitive for most people, they also agree remarkably well with measurements. Like it or not, they're here to stay. Special relativity was developed in 1905, and it was in the 1920s.
Wait 1 second. Somebody just, I don't know if somebody wrote a comment. Something just came up. I don't know if I'll be able to see. Oh, there it is. Stop ranting and give us the definition of time. The definition of time? The definition of time is a clock. You define anything using the measurement. Let me see, no, it's going to be impossible to open it. Oh my God. Let me see. Let me open this separately. Here we go. Let's go to this comment. This video. Which video is that?
All right, we're live.
How many views? 175 views. That's a lot. Oh, there's a bunch of comments. Oh my God. Stop ranting. Give us the definition of time. Reply. Time is defined by the way that it is measured using a clock. So a clock defines time. That's it. I don't know. Did I rant? Did I rant? Wasn't this really a short video? Yeah, I think this was the video the day before I came up with my new paper idea. So I don't know. This guy says never make another video again. I stopped watching this one. No more again. Oh my God. Oh my God. I'm one of those people that they hate watching. Why? I am recording my progress. What is wrong with that? I stopped watching this one. No more again. Oh my God. No. Okay. Let's continue.
In which a cadre of physicists worked out the rules of quantum mechanics. Initially, these two theories were invented independently, but if they were both true, then the two ideas needed to be blended together into a theory that is now called relativistic quantum mechanics. In 1928, British physicist Paul Dirac began that process. His equations predicted a new form of matter existed, what we now call antimatter. I talked about antimatter in another video, but the upshot is that the discovery of antimatter in 1932 by Carl Anderson gave physicists considerable reason to not only believe in quantum mechanics and relativity separately, but to also believe that Dirac had combined them properly. The 1940s brought with them a fuller understanding of the quantum realm. Physicists Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed what we now call quantum electrodynamics, or QED. QED is not only a fully relativistic quantum theory, it also quantized the electric field. In much the same way that early quantum mechanics showed that matter came in discrete packets.
Quantize the electric field. I mean, isn't an electron and a proton the quantization of an electric field? Didn't Einstein quantize light, which is the electromagnetic phenomenon? I mean, the quantization of the electric and magnetic and the electromagnetic field has been ongoing for a long time, no?
Not only a fully relativistic quantum theory, it also quantized the electric field. In much the same way that early quantum mechanics showed that matter came in discrete packets, QED showed that the electric field.
I mean, initially, Planck showed that electromagnetic energy, came in discrete packets. That was his H. Wasn't that? Isn't H the minimal energy packet or something? So didn't it all start with electromagnetic fields?
Also came in packets that we now call photons. If you feel that quantum mechanics and relativity have made unsettling claims about reality, quantum mechanics will give you an ulcer. QED describes two electrons scattering from one another as one electron emitting a photon while the other absorbs it. That's not so hard to imagine. However, the exchanged photons differ from the familiar massless photons of ordinary light. For one thing, the photons of QED can actually have a large mass. This is not a problem in the quantum world, which is governed by, well, among other things, the Heisenberg uncertainty principle. Boiled down to its essence, this principle says that extra energy can simply just appear for a brief moment, as long as it disappears quickly. The bigger amount of energy that appears, the shorter amount of time it can exist. Although the idea of massive photons already sounds pretty crazy, QED isn't done yet. If you follow that idea a little further, you'll find that QED predicts that nothing is really something. I'll wait while you process that last sentence. Nothing is really something.
Okay, that's just a problem with definitions. I mean, if nothing is something, then just redefine. Like that's just confusing terminology. So fix your terminology. So there's nothing to be proud of when your terminology confuses. Terminology is designed to not be confusing. So fix your terminology.
So let's see what that means. We'll start by taking this box, which is filled with air. The next step is to take all the air out of it and shield it so there are no external energy fields seeping into it. With nothing inside, surely it's empty, right? Well, let's start zooming in. Maestro, can you zoom a bit? Nope, not seeing anything. Maybe a little more? This isn't getting us anywhere. Time to pull out the big guns. Maestro, can you do the quantum zoom? The image you're seeing gives you an idea of the smallest quantum reality. The flickering colors represent the constant creation and destruction of matter and antimatter. Electrons and antimatter electrons, quarks and antimatter quarks, they are created from nothing and disappear back into nothingness. We can see that when we look at what is going on at the smallest and most quantum of scales, that empty space is actually extremely busy. Scientists have a name for these effervescent subatomic objects. They are called virtual particles.
I don't know why they insist on this virtual particles. He just finished telling us it's real. Now he's using a term virtual. That's, well, I don't know why they do this. They say one thing and then they contradict themselves. I would say that's one of the biggest problems with science and with quantum mechanics. These contradictions in the terminology.
There are lots of other ways to visualize this, but one way is to think of the foam on a particularly fizzy root beer.
Let me just check the audio. Yesterday the audio was such a nightmare. One second, let's see. It sounds okay. Let me make sure that it's the right. We're recording the correct audio. I did check in the beginning. Yeah, it looks like it's the correct audio. All right, let's continue.
If you look closely, you can see bubbles appearing and disappearing in an ever-changing way. For this reason, some scientists call these virtual particles quantum foam. Yeah, I know. This just sounds entirely impossible. So how do we know it's true? There are lots of reasons, but we can talk about two that are really totally cool. The first one is what we call the Casimir effect, first predicted by Hendrik Casimir. This effect is pretty easy to understand. The way it works is the following. Start by assuming that virtual particles exist everywhere in space. Now, take two metal plates.
That's a contradiction. Start by assuming virtual particles exist. So if they're virtual, then they don't exist. So what do you mean, start by assuming that virtual particles exist? Stop calling them virtual particles.
And put them near one another. Let's think about.
Look, just stop contradicting yourselves. I'm not asking for much.
What's going on?
Like, take a stance, and if you're contradicting yourself, then tell us. Well, it's a self-contradiction, but at least admit that you're contradicting yourself, because I don't know what to do with what you're saying.
You've heard that in quantum mechanics that particles have both particle and wave properties, and this is true of virtual particles as well.
Okay, so they're real. Why do you claim they're virtual? Why not? How are they not real? Especially now you're going to tell us about the Casimir effect, so they're measurable. So how are they virtual?
These virtual particles have both long wavelengths and short ones, and everything in between. Furthermore, they occur everywhere.
I don't think particles exist. I think all that we have is these tiny waves, wavelets. There cannot be a particle, because a particle would be a violation of Heisenberg's uncertainty. So there cannot be a particle. Also, it would contradict my intuition of gravity, of the flow of ether. I don't see how a particle can survive those speeds. So for those reasons, I think there's only waves or wavelets, tiny, tiny waves.
However, the plates introduce a new factor to the situation. Outside the plates, both long and short wavelength particles can exist. However, between the plates, long wavelength particles can't fit. Thus, there are more virtual particles outside the plates, and the imbalance causes the plates to move together. So what do we see?
So notice that like a radio wave can have kilometers long wavelength. So a single photon of a radio wave could be huge, kilometers on kilometers long. It could be the size of the solar system. A single photon, the energy of a single photon could extend over the entire solar system in length. So in that case, obviously it's not going to fit between the Casimir plates. So if it wants to show up, it can't. It can't between the plates, I guess. It could superimpose itself over the plates, like it could exist. If it's bigger than the solar system, so it doesn't care about the solar system. It flows through the solar system as if it's not even there. Okay, but what if it's a microwave, like 1 centimeter long, where a wavelength is 1 centimeter long, and you have a couple of these waves, let's say 10, 20, 100, 1,000 wavelengths composing a single photon, then again, it can't fit. Like even right, you could anyway. So it's possible to imagine why the Casimir effect should be measurable.
Well, when we do the experiment, we see exactly what Casimir predicted. This is considered very strong evidence for the existence of virtual particles.
You cannot, that's a contradiction. You cannot say evidence for virtual. That's just a contradiction. Stop saying virtual. That should be evidence that you should stop saying virtual. You can't say both. Now, some people, when they talk, they insist that these are virtual and they're not real. That you cannot talk this way. If you have evidence for something, then you have to stop saying it's not real. 1 second, let me check messages. Okay. What is this? Okay, I don't know what they're talking about. Oh my God. Okay, let me charge. This battery gets charged. Let's continue. So this is very important, because these science communicators, they keep confusing the public. So what is your purpose in life? To confuse the public? I mean, you cannot go on like this. This is just a terrible job. At least talk about the fact that you're contradicting yourself. Resolve, at least do something. You cannot say this is strong evidence for something that is virtual. Virtual means it's not real.
There is another measurement that supports the virtual particle idea. This has to do with the strength of the magnet formed by individual electrons. Electrons have electric charge, and they also act as if they spin. Just as in the classical world, a rotating charged object becomes a magnet. And because we know the electron...
So this is another thing, the fact that electrons behave as if they spin, and I heard that, but it cannot be, the spin itself cannot explain their spin, their magnetic spin, because they would have to rotate faster than the speed of light. I don't know, I don't understand that. I'd like to see the calculation for that. I don't know how this can be. Also, I don't know how a wave, right? An electron is a wave. How does a wave have spin? That's also very confusing.
Electrons charge and spin, we can predict the strength of the magnet each electron should be. When the prediction and measured strength...
Wait, what?
Just as in the classical world, a rotating charged object becomes a magnet. And because we know the electron's charge and spin, we can predict the strength of the magnet each electron should be. When the prediction and measured strength of the magnet formed by an electron were compared, there was a tiny discrepancy. They disagreed by 0.1%, 1 part in 1,000. A small effect to be sure, but a disagreement nonetheless. However, when the simple calculation...
So they predicted what the magnetic field of the electron should be based on what? I hate it when they say, oh, they made a prediction. Based on what? What went into the assumption? What assumptions went in?
Just as in the classical world,
so he's showing a ball, it's positive, and the electron should be negative. He's talking about an electron. Oh my God.
Formed by individual electrons. Electrons have electric charge, and they...
Oh my God, no one noticed this? Let me see. This is 650. I'm looking to see if anyone... This is 620. Has anyone... One second. Second. Okay, let's continue. Let's look for the word positive. I love how your electron has a positive charge. Yeah, 11 replies to positron. Positron. Anyway, it's a bug in the graphics department.
They also act as if they spin. Just as in the classical world, a
They
rotating
act as if they spin, okay? So they don't really spin.
charged object becomes a magnet. And because we know the electron's charge and spin, we can predict...
Wait, so we know it's charged and spins? You just said they behave as if they spin, so which is it?
predict the strength of the magnet each electron should be.
What?
Charge and spin, we can predict the strength of the magnet.
I'm lost. You said, so some people say they don't really spin, they can't really spin. So how do you make this prediction?
Each electron should be.
I'm going to have to assume that electrons do spin, and that's why they have a magnetic field. The question is, if they are a wave, how does a wave spin? I cannot imagine a spinning wave. I don't know what that would look like.
When the prediction and measured strength of the magnet formed by an electron were compared, there was a
The question is, are they spinning all the time? Do they have a magnetic field all the time, or only when this field interacts? So I don't think, since the magnetic field has to extend to infinity, so it cannot wait for an interaction. It always has to be in effect.
tiny discrepancy. They disagreed by 0.1%, 1 part in 1,000. A small effect to be sure, but a disagreement nonetheless.
Okay, so they made a prediction, I don't know based on what. So they must have assumed a certain size of the electron, a certain charge that they knew from experiments. And what about the spinning? How do you know how much spinning? I mean, you either measure the spinning or what? I mean, how do you predict the magnetic field from the spinning? So you know how much they spin? I don't get it. I just don't get it.
However, when the simple calculation was replaced by one using quantum electrodynamics and virtual particles, the agreement between data and theory was restored, and the restoration was better than anyone dreamed. The two numbers now agreed to 12 digits. This is the most accurate measurement mankind has ever made.
I don't get it. This makes no sense. This entire story makes no sense. At this point, I'm not following how they did the calculations, how they're doing the predictions, based on what? He's not saying what the assumptions are. He's not showing any equations, nothing. Just telling us a nice little story.
This incredible level of agreement is believed to be definitive evidence of the existence of the quantum foam. Now, let me whet your appetite.
The quantum foam even relevant to QED? And he doesn't even explain what QED is.
For something interesting. When we make a similar measurement of the magnetic strength of the muon, which is a cousin of the electron, the agreement is still good. It goes out to 8 places. But a disagreement appears in the 9th digit. While this discrepancy could be because of a faulty calculation or measurement, scientists are pretty confident that the disagreement is real. It could be the first sign that our theories are breaking down. Scientists are so intrigued that they've embarked on a new experimental program to better measure the magnetic strength of the muon. The G-2 experiment studied the muon for many years at the Brookhaven National Laboratory. Limitations in the existing accelerator complex led scientists to move portions of the accelerator and detector to Fermilab, which has the ability to make more muons and thereby study this phenomena more precisely. The G-2 experiment is expected to begin operations in 2016.
That's an interesting building. So that's Fermilab.
Or so.
This is like it's like a church. It's built like a church with this lake in the middle of this green valley. I mean, why not build more buildings, more facilities? Like, why are you stopping with one building?
We scientists are incredibly interested in the outcome of this experiment, as it may lead to a new and better understanding of the universe. However, even with this exciting discrepancy, we must not lose sight of the fact that the agreement between the predicted and measured strength of these subatomic magnets is spectacularly good. This agreement, combined with the observed Casimir effect, gives incredible confidence in the quantum foam. And the idea—
You're not explaining anything. You're just asserting. I mean, the Casimir you explained. Everything else you're not really explaining.
of the quantum foam leads to an entirely new paradigm, a completely different way of thinking about space. Empty space isn't empty. It's a bubbling, writhing, frantic place with energy converting to matter and back to energy again. Now, I understand that this claim sounds hard to believe, but this new view of the subatomic world is real.
No, it's not. Why do you think? Why would you even say it's hard to believe? I don't find it hard to believe.
And scientists can prove it.
But you didn't prove it.
You may never look
You just asserted it for 10 minutes.
at foam the same way again.
No, you haven't changed my mind about anything. You just ranted for 10 minutes straight. So people complain about me ranting and then you waste my time. That's not fair. I want my 10 minutes back. I'm looking at the names if I recognize anyone besides Don Lincoln. Wait, did you see Hubble? Hubble ESA. Okay, whatever. All right, next, quantum foam, 3 minutes.
Hi, welcome back to Knowledge on Ear. Today's topic is quantum foam. We'll visit this in 3 questions. What is quantum foam? How did we find out it exists? And why does it even matter?
Yeah, I want to know what the mass is, so that's useless. So I want to know the mass of the quantum foam. Can quantum foam ever be observed from 7 years ago? Quantum foam. 1 year ago.
In this video, we talk about what is quantum foam, and then I show you a number of clips from different modern physicists talking about the subject and how it relates to the laws of quantum gravity. So what is quantum foam? What is all this foamy, crazy stuff behind me here?
Quantum foam is an idea that emerges from the application of quantum physics to the fabric of space and time itself. You see, Einstein taught us in general relativity that space and time can warp and curve, and that creates the force of gravity. The idea is if you examine space on smaller and smaller scales, not everyday scales, but tiny scales, the uncertainty gets bigger and bigger, and space and time become foam-like. And that's quantum foam down at the ultra-microscopic scale, quantum foam.
So for the most part, general relativity describes big things, quantum theory describes little things, and that's the revolution that we found really powerful tools.
My brain is falling asleep. This is so boring. I need to calculate the mass of like quantum foam. Somebody help me. Okay. What is inside a proton? Empty space is not empty. What is quantum foam? 9 subatomic stories. The crazy world of quantum foam. Is interstellar travel? Physicists despairs over vacuum energy. A second when I say Peter, I meant Paul. Sorry, dark energy has got something to do with quantum vacuum. The physics of G-2, 8 years ago. Quantum gravity. What are virtual particles? 4 months ago.
Modern physics makes a lot of mind-bending claims, but perhaps one of the craziest sounding is the idea that at every point in space, subatomic particles are coming into existence for a fleeting moment and then disappearing again.
Oh, he's not saying virtual subatomic, okay?
These flickering and ephemeral objects are called virtual particles. A lot's been written about them with varying degrees of accuracy. Let's take a deep dive and see how they're viewed by modern physics. Pretty crazy. I mean, just look right there. Do you see particles appearing and disappearing? Nah, you don't. Neither do I. And you can be forgiven if you're skeptical. Of course, when we look, we're not seeing things on a truly tiny scale. Our eyes can't see things much smaller than a tenth of a millimeter. And even using the most powerful scanning electron microscopes, we can only resolve things.
That is a scanning electron microscope. How would it work? How does this thing work? It's mostly stainless steel, so it doesn't rust. It's probably dry air, so there's no rust. Lots of screws, so it's... is it a vacuum or is it pressure? Probably a vacuum inside. I don't know how this thing works. How does it work? So it's probably just a vacuum inside, and there's just an electron beam, and they fire it from one side and observe something. This is the observation. They're looking at crystals. This is probably the camera. Okay, this should be pretty straightforward.
Things about the size of atoms. On the scale of virtual particles, these things are pretty big. And that means these bigger spaces contain lots of virtual particles. When you add up all the positive and negative effects of all of the virtual particles they contain, they average to basically zero. That's why virtual particles aren't obvious to everyone. However,
Wait,
on the scale
what?
smaller than a tenth of a millimeter, and even using the most powerful scanning electron microscopes, we can only resolve things about the size of atoms. On the scale of virtual particles, these things are pretty big. And that means these bigger spaces contain...
What?
Nah, you don't. Neither do I. And you can be forgiven if you're skeptical. Of course, when we look, we're not seeing things on a truly tiny scale. Our eyes can't see things much smaller than a tenth of a millimeter. And even using the most powerful scanning electron microscopes, we can only resolve things about the size of atoms. On the scale of virtual particles, these things are pretty big.
Okay. So virtual particles are tinier than atoms. Okay. I mean, I don't know. I mean, if you have a photon of a radio wave, it could be huge. So I don't know why you say that, but it's fine.
And that means these bigger spaces contain lots of virtual particles. When you add up all the positive and negative effects of all of the virtual particles they contain, they average to basically zero. That's why virtual particles aren't obvious to everyone.
Why do you say that?
On the scale of virtual particles, these things are pretty big. And that means these bigger spaces contain lots of virtual particles. When you add up all the positive and negative effects of all of
bigger spaces?
These things are pretty big. And that means these bigger spaces contain lots of virtual...
Biggest? What? What is he saying?
Particles.
Biggish?
When you add up all the... these bigger spaces contain...
Biggish?
Lots of virtual particles. When you add up all the positive and negative effects of all...
I guess when we look at atoms, that's still a big place.
All of the virtual particles they contain, they average to basically zero.
Average to basically zero. They all have positive mass. There's no negative mass. So these virtual particles must have a combined mass. There must be a mass. Maybe the charge is zero. Maybe the momentum is zero, but the mass is not zero.
That's why virtual particles aren't obvious to everyone. However, there is no doubt that virtual particles are real.
Wait, so why do you call them virtual?
We can see them indirectly. If you take two conducting metal plates...
Conducting? I thought you need to take two non-conducting. If they're conducting, aren't you going to get like electric effect, magnetic effect?
Place them near one another. And I'm talking really, really close, like separated by a distance equivalent to the diameter of a handful of atoms. Those two plates will feel an attractive force. This is called the Casimir effect, and I've made videos about it. As always, the link is in the description. The Casimir effect works because the plates make it impossible for certain virtual particles to appear in the space between them, while outside, all particles can exist. This slight imbalance leads to a force that pushes the plates together. And here at Fermilab, we measure the spin properties of a subatomic particle called the muon. The particle's spin and electric
Oh, so the muon is positive?
charge mean the muon is also a tiny, tiny magnet. While the theory of 1930s quantum mechanics makes predictions of how strong the magnet should be, those predictions are wrong by a tiny bit, just 0.1%. This tiny shift is because each muon is surrounded by virtual particles, and the interaction between the muon and the virtual particles causes a tiny shift. The G-2 experiment actually measures the shift, and it does it incredibly precisely, like to 8 significant figures. The prediction and measurement agree quite well. And it turns out that there's a small disagreement in the last couple of digits, which could mean that there's more to learn about virtual particles, but that's the story for another time. I've made several videos about the G-2 experiment and the significance of the discrepancies. The links are in the description. But the real bottom line is that the Casimir effect and the accurate prediction of a 0.1% shift in the magnetic properties of muons are experimental proof that virtual particles are a real thing.
Yeah, but he's not explaining, he's just ranting.
But if they're real, what are they? And this is where
Virtual particles are real.
things get tricky. After all, empty space surely looks empty, not like a flickering, chaotic mess. So let's start with the simplest way of thinking about virtual particles. We start out with a truly empty space, which includes absolutely nothing. It has zero energy. I mean, really, nothing at all. Then, according to the simple picture, from that nothing, a matter and antimatter electron appear. That's because even with virtual particles, some of the usual rules apply. In this case, matter and antimatter particles appear in pairs. The two then quickly recombine and go back to zero energy. The pattern then repeats over and over again, sometimes simultaneously, with more electrons and antimatter electrons, quarks and antimatter quarks, muons and antimatter muons, until the whole...
But all these have a mass. So this thing has an average mass. So there is a vacuum mass. We shouldn't call it a vacuum. We should call it the ether. So the ether should have a mass density.
zoo of subatomic...
Like you could say the charge density is 0. It's neutral in terms of charge, of electric charge, magnetic polarity. Then yeah, it's neutral. But mass, and that's why the energy, it's a non-zero energy. It's zero energy is not zero. It's zero energy is positive. I mean, it sounds like the Higgs field. I don't know if the Higgs field is it. It might be.
Particles are represented, however briefly. The graphic sort of gives a sense of the vibe of what this model looks like, with things constantly appearing and disappearing. I guess you could maybe accept this, but let's just take a look at that first electron and antimatter electron. Initially, the space was empty with no energy. Then two particles appear, each with mass. Since mass equals energy, the result is that while the particles exist, the space has energy. And that seems to pose a problem, as the law of conservation of energy says that energy can't change. Yet here is a case where we started with no energy, then had energy come into existence before that energy disappeared again when the two particles annihilated. The usual explanation invokes the Heisenberg uncertainty principle.
I don't even think you need the Heisenberg uncertainty. All you have to say is that it has an average positive energy. There is a positive energy, there is a zero state positive energy, and there's a fluctuation around that positive energy. So it sometimes goes up, sometimes goes down, but the trend is some positive energy. So, and that's it. So it always has a zero state energy. So you don't have to say energy comes into existence and then disappears, because on average there's always particles running around. So on average, it has energy. It has mass and energy.
There are a couple of versions, but the relevant one is given here, and it says that the uncertainty in energy times the uncertainty in time must be bigger than a very small number.
Yeah, that's just a fluctuation. But the average energy slash mass is positive.
The relevance
You're talking about the fluctuations, the deltas. I'm talking about the average. Like a fluctuation explains if you have negative mass or negative energy to balance it. You cannot have, because on average, there's always stuff. It's not like there is a particle and then nothing. It's more like it's seething. There is no empty space. Everything is seething. Everything, it's always full of these fluctuations. There is this pressure. There has to be a pressure from all these particles. So that is the normal state. The fluctuations, the Heisenberg uncertainty doesn't really explain positive pressure. It could explain a particle pair appearing once in a while, but if there is a seething state, then that's not really explained. You can explain the fluctuations with Heisenberg, not the fact that you have a general positive, an average positive pressure. That doesn't make any sense.
here is that it means that energy can change as long as the amount of time that happens is short.
That's just the fluctuations. That's fine to explain the fluctuations, not the average. You cannot explain the average using Heisenberg.
The graph says it all.
The graph says just delta E times delta T is a constant. There's an inverse relationship between them. That it just talks about fluctuations. I could use the same thing for Wall Street. This is the way every natural phenomenon behaves once you determine a trend. There's always fluctuations superimposed on a trend. But you have to explain the trend besides needing to explain the fluctuations. The fluctuations, you know, that's fairly easy to explain, but the trend, that's it. Both are easy, but they need to have separate explanations.
If a lot of energy
So I don't know why. I mean, I don't think we know either one where this where the zero state energy comes from, where the average comes from, and where the fluctuations come from. I don't think we know.
appears, that can only happen for a very short time. If the amount of energy that appears is small, it can persist for a longer amount of time. Mind you, longer still means very short. You'll never see it with your eye. So, the Heisenberg uncertainty principle is indeed relevant, and this explanation is real. But it does leave a false impression of particles appearing and disappearing. I mean, this does happen, but to better understand the modern meaning, we should revisit what we mean by the word particle. And that brings us to the present way of thinking. The name for the most modern theories of the quantum realm is called quantum field theory, or QFT. There are many examples of QFTs. For example, the theory that explains electromagnetism is called quantum electrodynamics, or QED. The theory that explains the strong force is called quantum chromodynamics, or QCD. And I've made videos talking about both of these specific theories. As usual, the links are in the description. But I don't want to talk about these specific theories. I want to talk about the basic idea of generic quantum field theory. The gist of all these QFTs is that empty space isn't actually empty. It's filled with fields. It has an electron field, a muon field, various.
I don't see why you need these fields. These are just different types of waves, all waving in one field. I don't see why you need separate fields. I don't see how you can have separate fields superimposed on top of each other. I just cannot imagine it. What's wrong with a single field? I don't see the problem.
Quirk.
And the evidence points that it's all one field. because light bends due to gravity. So gravity is the ether field being dragged, and it drags light. So you see that it's all one field.
Fields, a photon field. In fact, there's a field for all of the known particles of the Standard Model. You might have seen this graphic that lists the known particles. That sounds super complicated, but let's start simple. Forget everything except the electron field. It fills space. In the classical world, it doesn't do anything. But in the quantum world, it can vibrate. And if it vibrates in exactly the right way, you have an electron. Indeed, that's what the electron.
Okay, what do you mean it can vibrate, and if it vibrates in exactly the right way, you get an electron? What do you mean it can vibrate? If the electron field vibrates, that is an electron. Otherwise, what is it? What is it if it's not an electron? How can it vibrate? How can the electron field vibrate and not be an electron? I don't understand.
Electron is a very specific vibration of the electron field. Precisely how it vibrates is determined by the properties of the field. It's like how the lowest note on a guitar string depends on the length of the string, the material it's made of, and how tightly it's stretched. So that's the key point. Electrons are specific vibrations of the electron field. Antimatter electrons are slightly different vibrations of the same field. Now we're getting to the main topic of this video, virtual particles. A quantum field can vibrate in more ways than the specific one that makes real particles. And when it vibrates in not quite the right way to make an electron, that's a virtual electron, although there is a corresponding vibration that also makes an antimatter electron. The same thing works with the photon field. Vibrations of the photon field make photons. Photons are different than electrons in that they can have any energy, but all real photons have zero mass. So for a real photon, the vibration pattern can have any energy as long as the energy vibration occurs in such a way that it has no mass. If the photon field vibrates in such a way that the vibration doesn't have zero mass, that's a virtual photon.
So virtual photons are non-zero mass? They actually have a mass?
And the same thing goes for all of the other particles. A very specific vibration of the up quark field makes up quarks, while other vibrations make virtual up quarks. It turns out that the various fields can interact with one another, but that's the topic of another video, so I won't go into that here. The bottom line is that quantum field theory postulates that space is full of a number of fields, each of which are vibrating in ways that don't create real particles, but the ensemble of vibrations are all the virtual particles that exist in that space. The line is that quantum field theory postulates that space is full of a number of fields, each of which are vibrating in ways that don't create real particles, but the ensemble of vibrations are all the virtual particles that exist in that space. They are the white noise of the universe, a quantum hum, if you will. That's it. Particles are special vibrations of fields, and weird vibrations are virtual particles. That's the gist of quantum field theory and how it explains the world around us. It's probably worth noting that quantum field theory is just that, the theory. It explains physical effects. It could be that the real explanation of how the universe works is something else. What we know is true comes from the measurements, like scattering particles, measuring the Casimir effect, mu on G minus 2 measurements, etc. Thus, the field theory is an idea, including the idea of vibrations, that's well tested, but it's important to remember that it's not the final word. Still, the idea is...
What do you... I don't know what you mean, that's not the final word. Nothing is the final word.
It explains physical effects. It could be that the real explanation of how the universe works is something else.
Yeah, that could always be true. Why are you bringing it up now?
What we know is true comes from the measurements, like scattering particles, measuring the Casimir...
Scattering. I don't know. You never spoke about scattering particles.
Effect, mu on G minus 2 measurement.
We need to look into mu on G minus 2. I don't know anything about that.
Etc. Thus, the field theory is an idea, including the idea...
The field theory?
2 measurements, etc. Thus, the field theory is an idea...
Thus, the field theory is an idea...
including the idea of vibrations, that's well tested, but it's important to remember that it's not the final word. Still, the idea is worth knowing. And I don't know about you, but I think that it's kind of good to know that the universe is sending us good vibes. Okay, that's some crazy stuff, but that's modern physics for you. If you like learning about this deep and kind of crazy sounding idea, be sure to share the video and subscribe to the channel.
Quantum foam, Sherlock Holmes, science at NASA 7 years ago. Quantum foam, how the universe randomly unfolds from quantum foam. Lee Cronin, 2 weeks ago. Who's Lee Cronin? I need to go get some coffee. I'm
At the beginning of
dying.
the universe, current physics would point to a Big Bang, right? And from that Big Bang, the rest of the universe unfolds. I guess we went from an expanding universe.
Lee Cronin, PhD. Regius Professor of Chemistry, University of Glasgow. Wearing red. He's gay. He's gay. His shoelaces match everything perfectly. Either he's gay or he wants everyone to think he's gay. I mean, that's gay. Everything is just perfect, impeccable. And big, what do you call these? Achilles? I don't know what you call it. Shin muscles? So he works out. Look at his thighs. Yeah, he's gay.
To matter being formed and crystallized, if you like, forming hydrogen. Hydrogen comes
Clean shaven, stylized hair. That's stylized. That's a haircut.
together. Under gravity produces stars. Stars produce galaxies. Planets get produced by exploding stars. And fast forward, life emerges on the planets, and we have technology.
Let's check. Is Lee Cronin gay? Lee Cronin, the boyfriend of Lydia Bright. That's a different Lee Cronin. There is Lee Cronin. Lee Cronin, born is the Regis Chair. He was elected fellowship. British. Let's see. Known for awards, fields. Okay, is he gay? What are you gay? Wife, no wife. Yeah, I don't know. Okay. Leroy Cronin. I don't know. Why is he wearing all red? I don't know. Who dresses this way?
And human beings and people lobbing stuff into space. Quantum physics basically shows you that the universe is actually quite random. Those random processes can, if you like, be harnessed in the process of selection. So quantum physics gives you like literally the possibility space for having fluctuations here, there, and everywhere because you're looking in a probability. It's like a field. What happens is those objects are produced. If they can then start to act on themselves or on other simple objects that are produced in the same environment, that's when the process starts. So you have this quantum foam, if you like, of randomness, and then this ability for copying to occur.
What is he talking about?
And that copying, whether the copies are allowed to live or not, is selection. And if the copies are allowed to live because the environment doesn't kill them, then that's evolution. And if you like, the quantum nature of the universe actually generates the random fuel for this to occur. So it's kind of insane in that the way you look at it is the universe.
Okay, words. I'm looking for a calculation. What is the mass of the quantum foam beyond the mechanical universe? Created by electric current. Torque. Is this wrong? Did AI, quantum foam, the smallest stuff, how to travel faster than Leonard Susskind? Quantum entanglement, quantum field, quantum. So, have we ever measured the weight, the mass of, like, quantum foam is consciousness? No, it's nothing to do with consciousness. Everything is consciousness, yeah. My socks is consciousness. Dodecahedral fractal animation. What if space is not empty? Quantum theory's most incredible prediction. The most beautiful theory, the quantum field theory.
भी लेखक है, पोएट्स है, फिलोसोफर्स है.
So it turns out that space isn't empty.
What? Really? Yeah.
Another day, another story.
Oh my God, 48 minutes. Keep going.
We can even see times where the.
Have you ever wondered what?
Okay.
Brian Cox.
Bathroom quantum field.
Hey everyone. The summer
This is Huygens optics.
Hey everyone. But then distributed among are presented in 2D, but 3 times 10 to the 79 space. Part of
represents a real physical difference in the field state. Okay, let's bring all of this together.
I woke up to these two very nice.
What I'm about to tell you is top secret.
Quantum foam units.
Conspiracy bigger than all.
You've heard about quantum entangled particles.
Physics. Flows create quantum
Good morning,
foam.
people. This is Kali, and today we're going to be talking about gravity. We have a thing. Yeah, go like this. As we do.
He's not talking.
Embark with us on a captivating journey into the heart.
Today's topic is quantum foam. What at quantum level?
Can somebody do a calculation,
Quantum
please?
gravity is a quest to unify.
Thank you. So it looks awesome. Thank you. She'll be running around as Ethan later. Nice. Oh, means I get to kill you. I'm kidding.
Between them, it's time we talked about.
What you are looking at is nothing. This is what occurs in a perfect, completely isolated vacuum.
Hello, my name is Sarah Astles. I'm the CEO of the International Space Federation. Thank you for joining us today.
In this equation, what is interesting is that we have in the first term on the left.
Okay, we're
Lives
gonna.
New Jersey's most famous foreign-born citizen, Professor Albert Einstein, who helped discover the atom bomb. Lives New Jersey's most.
That's a very uncomfortable chair. Could you think about sitting on that? Look at that. Maybe it is comfortable. I don't know. Doesn't look comfortable. New quantum correction photons. Most beautiful theory. Okay, we need to actually. I think YouTube is not going to help us. No YouTube. All right, whatever. Okay. All right. Okay, let's try and let's ask maybe. Let me log into ChatGPT. Log me out. Give me a minute. My God, I need to. What is that? Okay. I would was reaching out to see if you're interested in joining me at the thing developer conference in Champaign. We've worked hard to plan an amazing lineup of keynotes this Microsoft .NET weekend. I'm pinging you now because our standard registration rates. Okay, you're not inviting me to speak? You want me to join? No, I don't join. Okay, let's continue. Okay, how long have we been? We've been here for an hour and a half. Oh my God, this is so difficult. Here, let me give you a link. So, what I'd like to know. Okay, let's ask ChatGPT. So the question is, what is the mass of the quantum? Well, not the mass density. Density, also known as space-time foam, was introduced by physicist John Wheeler in 1955. It refers to the idea that at extremely small scales, on the order of the Planck length, 1.6 times 10 to the negative 5 meters, space-time is not smooth, but rather exhibits a frothy, turbulent structure due to quantum fluctuations. Why do they call it space-time? These fluctuations are thought to cause temporary changes in the geometry of space-time itself. Why do you need to talk about the geometry? How could you make a change to the geometry? That makes absolute 0.0 sense. What does it mean to make change in the geometry? Oh my God. The mass density of quantum foam is not a well-defined or directly measurable quantity in the way that the mass density of ordinary matter is. This is because quantum foam exists at a scale where the classical concepts of mass and density break down. What? What are you talking about? What are you talking about? You can either measure it or not. What are you talking about? And quantum gravitational effects dominate. What? What are you talking about? However, one way to estimate a related concept is through the energy density associated with the quantum fluctuations of spacetime. At the Planck scale, the energy density can be extremely high, on the order of the Planck energy density. What? What are you talking about? What are you talking about? This is a Google kilograms per meter cubed. A Google? That's the order of magnitude? What? How do you get that? C to the 5th power divided by G squared times H bar, the reduced Planck. This energy density gives an indication of how intense the quantum fluctuations could be at this scale. However, it's important to know that this is a theoretical construct and remains speculative without a full theory of quantum gravity. Oh my God, this is too high. This is an immense pressure. So if this pressure, if that's the pressure, isn't that too much? Why would how do they get this? Why is this the equation to define the fluctuations? I mean, don't they measure it? Don't they can't they tell me what they measured? What did you measure? You must have measured this, right? I mean, you don't measure it? In summary, while the mass density of quantum foam isn't directly defined, what do you mean it's not there? The concept relates to extremely high energy densities at the Planck scale. indicative of the intense quantum fluctuations in space. Okay, and we need to derive. Can you show me how to derive this? Well, what's going on? Okay. Common misuse. It's worth noting that oh, that's from the previous question. Okay, I'm too tired. I need to go make a cup of coffee. Otherwise, I'm dying. Okay, we'll continue later.